Next paper will be SRAIF, Self and Sparse-Reward Robotic tasks from pixels with active interference, inference, and Robotic.
Hello everyone, my name is Vietso, and I am from the Neuroadaptive Computing Lab from Rochester Institute of Technology. And today I'll be talking about our proposed agent who can solve Sparse-Reward robotic tasks from pixels. So here we propose a novel contrastive recurrent state prior preference model, which allows the agent to learn its own prior preference over the world states online. We also propose a new formulations of expected free energy, improving the stability of the action pattern. We also propose the self-revising active inference agent, boosting the model convergence rate in sparse-reward tasks, and so that we provide evidence that our agents outperform state-of-the-art reinforcement learning and active inference big science. So here's the model. Our agent is built on top of the world model. It has the following modules: so encoder posterior, decoder reconstruction, and transition prior. So first, it encodes the observation into an approximate posterior, and then it estimates the next state prior given the action in the previous state. And then finally, it tries to estimate the correct future observations using the decoder. So to learn this model, we utilize the active inference process theory framework. This resembles variational inference optimization, variational autoencoder, and world model inference learning. So in short, we minimize the variational free energy or marginal free energy that consists of two terms: complexity and accuracy. The complexity term is the KL divergence between the approximate posterior states and the prior orbit states. And minimizing this term means to reduce the amount of surprise over the latent representation. The second term is the accuracy term, is the negative log likelihood of the predicted observation given the actual future observation. So minimizing this term means to best estimate the future observations. So in active inference, the agent takes the actions that it believes would lead to preferred outcomes. So to construct this prior preference, we learn a deep neural network that dynamically produces the prior preference or the preference over states at each time step. So here's the architecture. We have the similar architecture as the world model, both having the encoder posterior and the transition prior. So the loss we use in here is the contrastive loss between the estimated preference state and the world model state. So when the agent is successful at a particular time step, we will contract these two states together, and then when it fails, we will repel these two states away from each other. So to do this, we introduce a prior preference rate called rho, which dynamically determines if each pair of state is repelled or contracted. So you can see here, this is an example of how we compute the prior preference rate. You can see that it is decay backward, depending on the states of the trajectories, whether it's failed or whether it is successful. So here's the qualitative results of the prior preference model. For each environment, the top row is the actual observation, while the next row is the prior preference prediction. So we can see that in here, our model learns to predict the goal observation at each future time step. And then finally, we perform experiments on three main problems environments: mountain car, metal world, and robot suite. The mountain car environment is a single sparse-reward task. Metal world contains 13 different robotic tasks, and then robot suite contains 2 different robotic control tasks. And here's the results. You can see our agent solved all the tasks. And then this also demonstrates that our agent achieved better performance than other state-of-the-art reinforcement learning and active inference agents. So that is everything. Thank you very much for listening. And if you have any questions, just reach out to me at the poster session. I'm happy to talk to you. Thank you very much.